Graphs are all about, finding ways to represent relationships between entities. So usually you have some class of entities, and you have some kind of relationship between them you want to model. And then you want to ask questions, about the nature of these relationships, and we'll see, this is very abstract, we'll see, what kind of specific questions you can ask. And what we'll see is a lot of problems, even though they're, from different domains and about different things, at the end they kind of, once you kind of remove all the irrelevant features and distill the problem to just the core essence, it's essentially the same problem. Probably the context you're most likely to hear about graphs in is social networks or something, right? So the idea is, you have a bunch of friends on Facebook or connections on LinkedIn, right? So the set of entities we're interested in here is people, and the basic language of graphs is that, first that this is kind of at an abstract level, then we'll talk about how to implement it in the program. The basic language of graphs is that you have these things called nodes or vertices. That's just a generic term, for something that represents an entity. You have a person, named Joe or something. We'll call it person A, right? And so when you see a visualization of a graph, usually, nodes are drawn kind of like these circles. And, we call them nodes, we don't call them, people, because, like I said, this may be abstract. Later we'll see how, nodes can represent something else that's not people. But, imagine for now it's a social network. Okay, so, the nodes represent people. So you have some people, you have A, B, C, D, for example. And of course, this could all be happening at very large scale, but let's assume you have 4 people, A, B, C, D. And now you want to model friendships between these entities. Between these people, you want to model friendships. So your relationship type that you're modeling using this graph is going to be, a friendship. Or, a connection, for example, on LinkedIn. Okay, so in this kind of abstract representation, you draw these lines, which are called edges. And an edge basically represents that the relationship is present between the entities. So for example, B and C are this direct link between B and C represents that B and C are friends. And likewise, if A and B are friends, then you also have a link between A and B. And then maybe, C and D are friends, and C and A are friends. But A and D maybe are not directly friends. Then let's think about a question that LinkedIn, LinkedIn often asks, which is how far away are you from being connected to a person, right? Are you a first-degree connection? Are you a second-degree connection? Or are you a 3+ degree connection, right? LinkedIn shows you that information. So this is what's called a shortest paths problem. So what we're asking here is basically what is the minimum number of kind of indirect hops that are required to connect two people. So if I want to know, if I start at A, I'll call this my start node, and if this is my destination node, here I'm asking essentially what is the minimum number of hops of these intermediate links that are required to get from A to D. And so this is called the shortest path from A to D in this graph. So the answer here is, if you count the number of edges, 1, 2, you can get it added this way, or, well, that's actually the only option. So, 1, 2. But if there was, if you ask the question about A and B, the answer would just be 1. So this is, classic problem about graphs, but when you kind of you might be thinking about it in terms of people and connections, but as you kind of back away, you might realize that this applies to other things. For example, let's say that now we are in an airport, like a plane, kind of like airplane scheduling, flight planning. You want to get from, let's say these represent direct flights between cities. So now we're backing away from the domain of social connections, And instead, let's say A, B, C, D are cities. And these connections represent which cities have a direct flight between them. And I want to, and when somebody asks me for a flight ticket from A to D, I want to find, the fewest stops possible for them. Yeah, and I want to find the smallest number of stops possible for them. And so, again, this is actually the same problem. So even though it's a completely different domain, it's the same problem. So this kind of, helps you see that, essentially the whole power of graphs and like the reason people use them is because it allows you to kind of abstract problems away from their domain and into kind of like this abstract realm where we kind of already know how to solve like many types of problems. And so for graphs, as we'll see later with the breadth first search algorithm, there's an algorithm. You can apply it to find the shortest path. Now, there are different types of graphs. So this graph is the simplest possible kind of graph. It's what's called an undirected, unweighted graph. So what that means is, well, first, these are two attributes and they're kind of independent of each other. A graph can be directed or it can be undirected. Undirected basically means all relationships are bidirectional. So for example, we're saying that, if A is a friend of B, then B is a friend of A. So, this is like a property of the relationship that's being modeled. Not all relationships have this property, right? For example, A follows B is not the same as B follows A. But A is a friend of B is the same as B is a friend of A. At least on, most social networks. Likewise, we might wonder if, we really modeled, for something like a flight planner, we might wonder if we modeled this in the right way, because it's probably possible for there to be probably if there's a flight from A to B, there's also a flight from B to A, but maybe maybe we want to solve it only on a particular day, and maybe on a particular day there's only a flight from A to B and not the other way around, right? So, we might want to add directions to the graph. And so, when you have a directed graph, you kind of get these arrows here. And the arrow basically just says in which direction the relationship goes. And so, you get to define how you want to see the relationship. So maybe an arrow pointing from A to B, probably most logical to say that means there's a flight from A to going to B. But you could define it the other way around if you wanted to. You just have to be kind of internally consistent within your definitions when you, solve the problem. We could give all of these kind of directions. And of course, sometimes you may have a situation where something really is bidirectional while other things are unidirectional. And this is not a problem. The way that's typically modeled is, let's say there's a flight from C to B, but also a flight from B to C. So no problem, just add an edge in the other direction. So again, basic graph terminology, these are called nodes or vertices. These are called edges. Edges can be directed or undirected. A graph that has undirected edges is an undirected graph. A graph with directed edges is a directed graph. And as you might notice, a directed graph is essentially a generalization of an undirected graph. Why is that? Because imagine if every relationship is bidirectional, you could just, model it like this, right? We could if we want to indicate that every relationship is bidirectional, we can feel free to model it as a directed graph like this. But, then we have some extra data that maybe we don't otherwise need. But by and large, directed graphs are just a generalization. It allows, if you think about something like a road network, right, or it starts making a lot of sense, right, maybe most roads are bidirectional, true, but some roads are unidirectional, and you want to have a way of modeling that. Okay, now there's another thing you might have noticed about kind of the hypothetical flight planning idea, right? It would be a pretty bad flight planner that just gives you the flight with shortest hops. Because, well, first of all, what if there's a tie, right? What if, just for simplicity, I'm going to go back to the, unidirectional idea. So, hey, let's assume that this one is, let's assume this one's San Francisco, and this one's Tokyo, and this one is Phoenix, and this one is Austin or whatever. That's in Texas for people who don't know. So anyway, let's say the available flights look like this. Like, I want to get from SFO to Austin, and yeah, I know there's a direct flight there, but like, suppose there isn't, right? Hypothetically, I don't want to invent like obscure city names. That's all. Okay, so let's say there's a flight from SFO to Phoenix. Well, let's model it as undirected for now. Let's say all the flights go in both directions. And let's say there's, this flight. But let's say there's also, this flight. Now, first of all, one of the problems may be that the shortest path to Austin is of size 2 from SFO. But if you only consider, the number of hops, then for you, this path seems as good as this path. But, on a map, if here's like the US, Texas is here, SFO is here, Phoenix is here, but Tokyo is like way over here, right? So, what do you want? Do you want this flight path, or do you want, this flight path? I think you can kind of see where I'm going. So maybe there's, some other criteria than the number of hops, right? Like maybe you'd like to minimize, say, the number of miles, right? Okay, so this leads us to an idea called a weighted graph. So in a weighted graph, the edges are just augmented with an additional piece of information called the weight. And again, this is a generalization of, the most basic graph type, like unweighted, because, as we'll see, an unweighted graph is basically a weighted graph where every weight is 1. So we can label each edge with a number. So let's say, we'll label it with a number of miles. I don't actually know how far away these destinations are, so hypothetically, let's assume it's, 5,000 miles here. And, this is 6,000 miles. I know these can't be accurate numbers, but for example, and this is, 500 miles, and this is another 500 miles. So now we can kind of ask the question, find the shortest path from SFO to Austin where shortest is not defined as the number of hops, but is defined as the sum of the weights to that path. So here we'd be looking to discover this path, because its sum of the weights is only 1,000, which is much, much smaller than 11,000 miles. So, you can, and it's not only for breaking ties, right? You might have a situation where there's actually, for some destination, hopefully you don't have too much of this kind of air travel, but maybe you have some destination where taking 3 flights is actually better than taking 2, right? Because maybe the 2 flights are just kind of really bad, but the 3 flights are much more directed, I don't know, maybe you can either take 3 small flights or 2 flights halfway across the world, and the 3 small flights are actually minimize your mileage, and maybe you don't even want to minimize your mileage. The point is you can model this problem however you want. You can put whatever weight you want, and what we'll try to get is an algorithm that just on this kind of abstract representation finds the path from the source vertex to the destination vertex with the minimum sum of weights. And you can attach whatever weights you want to that. You could make it miles, you could make it about travel time. Let's say, thinking about air travel, this is just to kind of give you an idea, how you might go about modeling problems with graphs. So I'm thinking, okay, so for airline travel, definitely making every weight 1, which is, if you make every weight 1, what happens, by the way? This is kind of a good, thing to see. What happens if we make every weight 1? Well, if we do this, then the total cost of the path, right? What is the total cost of any path? If every weight on every edge is 1, the sum of the weights along a path, for example here to here or here to here, is just the total number of edges, right? So this is the same case. If you set every weight to equal 1, this is actually the same case as the unweighted graph case. So if you just like, so again, this just points out that like a weighted graph is a generalization of an unweighted graph. If you take a weighted graph and just assign every weight to 1, that's the same as an unweighted graph. Because then if you do ask for something like shortest path, the cost of a path is just the number of edges in that path. So putting weights on paths is basically just a generalization. And to give you an idea of like, how you might think about modeling, well, okay, we see that putting a weight of 1 on everything, that's just number of hops, bad flight plan. Also, number of miles may not be that great either, because number of miles doesn't take at all into account the fact that stops are annoying, right? So you might settle for a hybrid approach where, and this is kind of an arbitrary heuristic, but like just an idea, right? Let's label each edge with basically a mileage number that is not the true mileage, but is, let's say, 1,000 plus the true mileage. So for example, if Tokyo is, 5,000 miles away, we'll add 1,000 to this. And if this is 6,000 miles away, we'll add 1,000 to this. And, we'll add 1,000 to this and 1,000 to this. And what's the point of this is, well, what will be the final cost to get from the source to the destination? It'll be the true mileage, right? These mileages will still add up. Plus, you'll have kind of like this penalty factor of 1,000 times the number of hops. So the algorithm will see as the cost from one point to another as being basically the true mileage plus a penalty factor of 1,000 times the number of hops. And it'll optimize and find the path where, that total function is minimized. Like the total of the true mileage plus that penalty for having more number of hops. So then it means that, like, let's say you have one path that has 2,500 miles and 2 hops, it'll have, some cost like this. And if you have a path that is only 1 hop, but 4,000 miles, then that will actually be seen as, inferior. This will have a higher cost than this other path that has more hops but a shorter mileage, for example. So this just gives you an idea of like different ways, like you can assign weights to graphs in clever ways to optimize various objectives that you might have.
So you assign weights to edges.
Yep.
Is there a way that we assign weights to nodes as well?
Good question. So the question was like, why do we always assign weights to edges? Why not nodes? So for now, I'm going to say that basically the real reason is that the concept of assigning weights to edges, as we'll see at a later time, maybe not even today, but we'll see at a later time that assigning weights to edges is actually more general than assigning weights to nodes. So in other words, there are actually tons of problems where it's useful to think of it as the nodes having the weight and not the edges. But what we'll see is there's always an easy way to convert that into a representation where the edges have the weight. So, and like basically for that reason, we want to develop algorithms that consider weights on edges primarily, so we kind of solve the more general case. But that, you'll kind of get a better hang for this as you learn more and you kind of see examples of some of those algorithms. Yeah, so it's perfectly valid to think about vertices having weights, like that comes up in a lot of context, but usually you kind of just transfer those weights onto the edges. Okay. I know for sure we'll see such problems, maybe not today, but like in the upcoming follow-up sessions for sure. I can think of at least one problem I plan on doing that will essentially have weights associated with vertices that will just then convert to a format where weights will be associated with edges.
Is it possible to have a graph where there is a vertex that's not connected to any other vertex?
Absolutely. Yeah, so there's no requirement for graphs to be connected, and this is like another terminology concept that's good to know. A graph is called connected if there's basically a path from every vertex to every other vertex. Path is exactly what you think. Like in a graph, what I mean by path is, this. Like a path is some sequence of vertices, like A to B to C. It's an ordered sequence of vertices such that every pair of vertices that appears adjacent to the sequence is connected. So like A to B to C is a path. Now, we say a graph is connected if there's a path from every vertex to every other vertex. Like in other words, in the undirected graph case, we won't talk about right now like what it means to be connected in the case of a directed graph case, because that's actually trickier. But in the case of an undirected graph, connected basically means that everything is part of the same chunk, like this. Can you have a graph where like there's some vertex f out here that's not connected to anything? Like absolutely. And this graph is said to be not connected. Like we can say that this piece of the graph is connected, and this is a separate piece. We'll call that a connected component. And that actually kind of brings me right into the sort of one of the next topics in just a couple of minutes. Okay. So, we've seen how we can model some problems using shortest paths on graphs. And, for the case of shortest paths, I just want to emphasize that, like, absolutely you can combine weights with directionality as well. Like, for example, let's think about how to do, routing on roads, right? So okay, it's true that, like, Google Maps solves this problem in a slightly different way just because they have to solve it at such massive scale. But let's think about how, like, a basic app for, like, road navigation would work. So, and we can model this using graphs and solve it using the graph algorithm. So, you have some, like, streets, basically. And, streets may intersect in various ways. Occasionally, there may be some kind of weird, like, three-way intersection. Now, let's say you want to find out, I started some point A, and, and I want to get to some point B. And I want to find out what is, like, the best navigation. Like, should I go like this? Should I go like that? Right? Should I go like that? This is essentially the problem that Google Maps solves. Well, good news. We are actually able to solve this problem using graphs. So, if we want to solve this using graphs, like, basically what we want to do is we want to model, it'll be most convenient to just model street intersections as, basically model street intersections as nodes. So, what we can do is, let's call this something else. Let's call this, like, source and destination. And one way we can model it is we'll identify all the street intersections. So here's A, B, C, D, E, F, G, and you got like H and I here. Okay, so here's a bunch of street intersections. And basically what we can do is we can put them in a graph, and we can create edges between them that represent some metric, like maybe distance, like maybe the Google Maps minimizes like the distance you take. If you have like real-time traffic data, it's probably better to put minutes, because people really want to minimize the time. They don't care as much about distance, right? So it's up to you how you model this, but like ideally it would be something that like helps your users, right? Let's say it takes 3 minutes to get from here to here. Then you would create this kind of edge that is, telling you it takes 3 minutes to get from here to here. Why do we model why is it that as the entities we model, the street intersections? It's because those are like kind of the decision points where you have to figure out like where to turn or not to turn. If you're new to graphs, it may not be obvious to you that that's the modeling decision you could have chosen. You might have been thinking, okay, shouldn't I, maybe choose like a road segment as the entity to model? The problem is a road segment is not a specific location, right? So starting at a particular road segment, I can't tell you how long it takes to get to your destination because it depends on whether you're like right here or right here. So street intersections are kind of a sensible thing to model the connectivity of. If it takes 3 minutes to get from A to B, we kind of create this in the graph, and let's say it takes, 4 minutes to get here. So this is just kind of an abstracted representation. Like this is like a kind of a map, And this is an abstracted representation of what actually matters for purposes of solving the routing problem. This is the graph, okay? Let's say this takes 4 minutes, so, we'll have this. These kind of things lead to nowhere, so they're actually not important here. So we don't even have to model this. Then, you can go for, let's say you can go from D to I in 6 minutes. So, we have something like that. Let's say that this takes 2 minutes. And let's say, this takes 5 minutes and this takes 2 minutes. So A to G is 5, and this is, 2. And did I get all of them? Oh, well, there's also this D to E. I'll just give it like 4 and 4. And let's say this one takes 1 minute or something. So here we go, I missed this stretch of road too. Let's say this is 10 minutes. This is like extra slow for some reason. And, so then here's your graph representation of this, road network. And what these weights are representing is how long it takes you to get from one place to another. And let's say additionally now, there are some roads that are one way. So let's say, for example, this road is one way. So what would happen is, what we could do is we could, add directionality to these nodes. Like we could make this edge directed, and the other edges we keep bidirectional. So in a directed graph, we basically would just kind of duplicate all the edges to, you'll have an edge of 4 going this way and an edge of 4 going that way, which basically means you can traverse either way in 4 minutes. And it could be, also happens in maps all the time that, maybe this direction takes 10 minutes to travel because it's blocked up in traffic, right? But maybe Google Maps knows that this opposite direction is only 5 minutes. And so weights going in different directions can also have different weights attached to them. So, assume that for the ones I did not duplicate, they're just bidirectional with the same weight. And these other ones are, unidirectional. So here, C to D is one way. That's why there's no edge in the opposite direction. And here, this edge exists in the 2 directions, but is of different speeds. And so, this weight is 10 and this weight is 5. And now we can basically ask, again, kind of like this weighted, directed problem on this graph. If I start at the source, how long does it take me to get to the destination? Well, wait a second, there's one little complication here, right? Which is that the source is not actually anywhere on this map. But that's actually simple to handle. Basically what I do is I, consider that my first starting point, if I'm at the source, I have to go to either G or A. So basically I just try, I can just try all of these. I can say, okay, I'm going to try going from A to, and this one, you can see from this one that you have to get to D. So my routing problem is going to be, start here and get here. Or you can start here and get here. And then there's if I calculate that this stretch of road takes 4 minutes and this stretch of road takes 1 minute, what I want to do is I want to calculate the shortest path between G and D, and I want to add this 1 minute to it. And then I want to calculate the shortest path between A and D, and I want to add these 4 minutes to it. And then I'll just choose the shorter of those two. So that's how, something like that works. And then, of course, here, once you have this graph representation of your road, here, you will have to solve the weighted, directed shortest paths problem. What is the shortest path to get from here to here? And we'll see what the actual algorithms for that are. For the weighted case, it's a bit more complicated than the unweighted case. So we are not going to solve that one today. Today we'll see how to solve shortest paths for unweighted graphs. Okay, so this is one class of problems you can solve. And, again, I must emphasize, the whole point of graphs is basically to kind of take, things that are domain specific and abstract them away into these, abstract views of the concept, and then, and then just solve it using a generic algorithm. All right, So so far, like that was, I talked about shortest paths. Shortest paths, very useful. Like shortest paths problems are everywhere in computer science. Very useful concept. So that's one thing you can do with graphs. So you can do shortest paths. I want to discuss, a couple of the other ones. Just at a high level. So shortest paths, we saw we can, ask this problem about undirected or directed graphs, and we can also ask this about weighted, or unweighted. Like, we can ask this problem about weighted or unweighted, and we can ask it about directed or undirected. As we'll see when we do the shortest paths algorithm, it doesn't really matter much to the algorithm whether the graph is directed or undirected. Now, yes, of course, the algorithm will have to consider that piece of information because obviously the answer can be different depending on whether you can, travel a road from A to B or not, or whether the road only goes the other direction. Yes, of course, the answer is going to be different depending on whether your graph is directed or undirected, but it turns out to be very, very easy for the algorithm to consider that aspect, and it doesn't fundamentally change the character of the algorithm at all. Now, for weighted and unweighted, that's actually, as we'll see, that's like a much bigger distinction. It basically requires a different algorithm to solve it. The weighted case, or the unweighted case, will be solved by breadth first search, but the weighted case will require a more complex algorithm known as Dijkstra's algorithm, which is basically an extension of breadth first search to work for weighted graphs. And those two algorithms are pretty core graph algorithms. Breadth first search and Dijkstra's algorithm. Pretty core, like shortest paths problems are just kind of everywhere. And so this is like, one of the core graph topics you should know. Then another core graph topic is what I'll call connected components. Or think of it as connected islands. So this problem takes the following form. So imagine you have, imagine you basically have like a satellite image, some satellite imagery, and let's say you have a grid of pixels. Now, of course, maybe your grid is very big, but just for simplicity, I'll make it small. So, this is a grid of pixels, and basically, let's say it's an image of the ocean, and there are some pixels that are green or brown. It's like indicating an island or something. Green, brown, black, whatever. And, most pixels are blue. It's just the ocean. And I want to know how many distinct islands are in this area, like how many separate islands, right? And so this kind of touches on what, somebody asked about earlier. So the connected components problem is going to be kind of something like this. Here's our grid, and we want to know how many separate islands, how many separate connected pieces are there. So somebody asked earlier, does a graph have to be connected? Absolutely not. And in fact, in this problem, the whole point is that it may not be connected. So here, how do we model this? Well, first we have to say, what do you mean by connect? What do you mean by to say that something is a single island that is connected? So we might take it to mean that 2 pixels. If 2 pixels are island pixels, like these darkened ones are land, if 2 pixels are darkened pixels, then they are connected if they are, adjacent to each other in any of the 8 diagonal directions, any of the 4 standard or 4 diagonal directions. So here, we would actually represent it like this. These pixels are all connected to each other. Let's say, let me give kind of another pixel. So here, only this one is connected. So these are being represented by this graph representation, and these are being represented by this graph representation. So, and so this is our graph, both of these are our graph. This is our total graph, and we want to know how many connected pieces are there. It may not be completely obvious because we haven't discussed the algorithms yet, but this will actually be solved by the same algorithm as the breadth first search, as finding, unweighted shortest paths. And, if you think about it, it doesn't seem that crazy that it would be the same algorithm, because what is this fundamentally about? What defines whether a piece is connected? It's whether or not paths exist between things in the, these 2 vertices are connected because there exists a path between them. Now, in the case of shortest path, we insist on really finding the shortest path. Here, we only need to know that a path exists. And as we'll see at some point, maybe not today, that actually does give us more options for what algorithm we use here. So here you could use this algorithm called breadth first search, or Dijkstra's algorithm for the weighted case. For the connected components, you can actually, like, there's a couple other choices, like there's this algorithm called depth first search that also does it. Because those algorithms don't have to find the shortest path, they just have to find that there exists a path. And another thing that's, of course, different is in the shortest path problem, we pick a source and we pick a destination. Here, it's kind of asking it about kind of all pairs of vertices, right? We don't explicitly have to find if all pairs are connected, but the way the question is phrased, it's kind of all about, the overall behavior of this total cluster. So, connected components, what kind of graphs are we going to ask this for? If there were weights in this graph, they would kind of be ignored because this is about connectivity. So any weights would be ignored. So primarily this problem is about unweighted graphs only. And how about directed or undirected? Well, the problem with directed graphs is, let's say you have something like this. Now, let's say I ask you if A and B are connected. Well, like, that's kind of a hard thing to know, right? I mean, you have to define what you mean by connected, because it's true that B is reachable from A, but A is actually not reachable from B. So instead of saying that A and B are connected, you might want some concept like B is downstream from A, right? You don't really want to say A and B are connected because you actually can't get back to A from B. You want to say B is like downstream from A. And there is kind of like some theory, this is called strongly connected components, where you can kind of make this connected components question well-defined, and then you can kind of classify nodes into either, being upstream or downstream from each other, or being on the same level. Like, for example, here, we would say that A and C are on the same level, but B is downstream from them. But this is kind of a more advanced topic, and I don't actually anticipate covering this today or in upcoming classes. Or in any classes that are upcoming, like, immediately, I think. So, for the most part, like, for the standard definition of what it means to be connected, this only makes sense for undirected, unweighted graphs. And this will actually be solved by the same algorithm, BFS, which is why BFS is, like, so important and solves so many of these important problems. And going back to the fact that graphs are in general like a useful abstraction for different domains, let's say that this is no longer the problem. Let's say the problem is instead to make the Photoshop, that Photoshop like magic wand thing, right? So how does that work? You click on a pixel and it kind of spreads the neighboring pixels, right? So, the way you might imagine something like that is, okay, so you have a grid. You have a grid, and it's a grid of pixel values. Let's, ignore color channels for now. But, you have some kind of grid of pixel values, like this pixel has value 8, this pixel has value 10, this one has value 12, 3, 100, and so on, right? So the idea would be that if two pixels are adjacent to each other and sufficiently similar in value, you would represent them as being connected. So for example, let's say we have a threshold of 5. So if pixels are within 5 of each other, they are connected. So then here, the pixel 8, this one would be connected to this 10, which would be connected to this 12, and also here. So if pixels are like, adjacent to each other and also similar in color, they are connected. But for example, this 2 is not connected because it's more than this threshold. And this 100 is not connected. And then when you apply the magic wand, well, hey, it's the same problem. Right, because you clicked on a pixel, let's say you clicked on this 10, what I want to know is what are all the connected pieces, and then which one did I click on? Now, technically, I don't even need to know what are all the connected pieces. I only need to know what are all the pixels in the connected piece that I clicked on. And that's, once again, solved by breadth first search, as we'll see. Okay, before we go into breadth first search, I want to talk a little bit about like a couple more types of graph problems. So you have these all problems that I've passed. Here's a different one. Here's one of a pretty different flavor. I'll call this like dependency ordering. And this is kind of, if there's 3 kind of like important graph algorithms to know, I would say it's kind of like or not algorithms, but like graph topics to know, I would say it's these three. Like shortest paths, connected components, and dependency ordering, which is solved by an algorithm known as topological sort. And what is that? So dependency ordering, this is all about directed graphs, and it's about basically, let's say you're going to compile, a piece of code, right? You're going to compile a piece of code, and it has dependencies on other libraries. For example, library B has a dependency on library A. And so does library C have a dependency on library A. And then maybe my piece of code D that I want to compile has dependencies on both of these. So this is called a dependency graph. Notice that the dependency graph is kind of fiercely directional. What I mean by fiercely is it's actually anti-symmetric, which means that, like, if there's an edge from A to B, there's never an edge from B to A. Because, like, that would be a circular dependency, right? If B is dependent on A, then A cannot depend on B. And so this kind of represents that sort of like data flow. And here, the dependency ordering problem is basically to find an order. It's very easy to see by eyeballing this, but for a more complicated case, to find the order in which these can be compiled. So in this case, like if the arrow means depends on, there are basically two possible solutions. Either you compile A, B, C, D, or you can compile A, C, B, D. You do have these two choices, right? First you have to compile A before you can start compiling either of these. Then these two are actually independent, so you can compile them in either order. And then D has to wait until both of them are done. And, a highly, highly related question is you might, instead of just getting a linear sequence like this is called a topological sort, you might get something called, you might, well, I don't know if this really has a name, but a sort of layering of the things that can be done in parallel, right? So like A has to be done first, and these two could be done in parallel, and then this has to be done next. So like, get a kind of layering into stages, and the topological sort algorithm can also do that for you. So, dependency sorting, it doesn't even make sense for undirected graphs. Dependencies are all about having a direction. So this is for directed graphs. And then, weights really have nothing to do with this. So primarily this is defined for unweighted graphs, but, we can think of like weighted variations where, for example, let's say, we can think of weighted variations where, for example, let's say each of these vertices is associated with a weight. So here would be a case where every vertex is a weight. This is like how long it takes to compile this library. So this one takes 5, this one takes 5, this one takes 9, and this one takes 3. And you could ask something like, what is the critical path? Right? What is the slowest path? Because this won't, D can't compile until like all of its prerequisites have finished compiling. So what is the critical path, right? What is the path that if I optimize, the overall process will actually go faster? Or, actually, topological sort, historical note, was invented in the context of essentially project planning. So, basically, you can view the tasks of, say, like a construction project or a software project as having this kind of thing. Like, some things must be in place before the next stage can start. And so you can view like an overall task, you're building a building or writing software, as being this kind of flow, right? Where like something has to get done before something else can happen, and these are dependencies. And then you might ask a question like, what is the critical path of the project? What is the path that is like most slowing me to completion? And it was actually in that context that topological sort was invented, in like the early 60s or so, is my understanding. And this is like another critical problem, like, sometimes, people tend to like sometimes criticize like the algorithmic interview, right? Like, these interviews that ask you like hard algorithms questions, people are like, well, when do you actually have to do that on the job? But actually, like, so for some algorithms I can understand the case for that. Like, dynamic programming or something like that, it's pretty rare to have to do that on the job. But like actually speaking the language of graphs, like understanding ideas like routing and shortest paths, understanding dependency ordering and things like that, Like, these are things like I have personally had to do on the job. Like, I definitely have like owned a software component before that had some implementation of this in it. It was like a parallel implementation that's a bit more complex than like the standard version of this algorithm, but it would have been pretty hard to understand if I didn't even know the basic version of the algorithm. And, you know, things like this, I mean, I've seen them even in like, I don't know, I once played this game where like, you know, you had a spaceship and you could kind of like jump to like star systems on a star map, and the way it calculated which jumps you would do is basically by like a shortest path algorithm. So if I had written that game, you know, I would have used this. So, you know, these kind of like problems are like everywhere in computer science. Connectivity, shortest paths, dependency ordering. Like these are like, I actually do believe these are like genuinely important for a software engineer to know. Okay, so I'm just about done with this kind of like high-level overview, but you know, just real quick, like 2 more that we're not going to cover in like any detail, and I don't plan to do any kind of like course. Well, I don't at the moment plan to do any sessions on. There's this one called spanning tree. So this one is it comes up a lot in coding contests and stuff, but I haven't really seen it much in actual practice. I mean, I know it is used for some things, but spanning tree is something like this. Like, let's say you have a network of computers that are connected like this. So a spanning tree basically asks you to delete the redundant nodes, as many as possible, so that the network is still connected. So here, like, if you get rid of this edge, and you get rid of this edge, and you only have these left, the network is still connected. And this can be asked for like a weighted or unweighted problem as well. You know, it's only for undirected graphs pretty much, but you can ask it for weighted or unweighted. And in the case of a weighted problem, it's a little more complicated because it has to delete it basically has to delete the most expensive edges. So that's just like another one. You know, so this one is for undirected, and you know, you can do it for weighted or unweighted. And you know, last one I'll just mention, you know, in case you ever see this kind of problem, maybe you'll know what to look up. It's this thing called bipartite matching. So this is kind of a pretty advanced topic, but you know, the idea is, let's say you have like n people and n jobs. So let's say you have person 1, person 2, person 3, you know, person n, and then you have some jobs, like you have job 1, job 2, job 3. Well, let's say I do it with 4 people. And basically what you want to do is you want to create a one-to-one correspondence between people and jobs. So like, basically you want to assign every person to a job. A person can't do multiple jobs, and a job can't be done by multiple people. Like, so you want to create this like one-to-one mapping of people to jobs. But the trouble is, not everybody can do every job. So here, your edges would basically be modeling which people can do which jobs. So let's say person 1 is capable of doing job 1 and job 2. And person 2 is capable of doing every job. And person 3 can only do job 3. And person 4 can do 2 and 4. So you have this kind of crisscrossing graph where things on one end of it, like people, are matched to things on another end of it. And this style of graph is called bipartite because it has essentially 2 parts. There's no relationships between people to people, and there's no relationship between jobs to jobs, but people are matched to jobs. And this type of graph is called bipartite. And bipartite matching is basically asking, can you find a one-to-one mapping of people to jobs that satisfy these constraints, you know, such that you actually fill all the jobs, right? So you have these constraints on which person can do which job, and you want to find a matching between people and jobs so that you fill all the jobs. And you can also do this in like a weighted problem where, you know, maybe the jobs are associated with a weight, and then here it would be like, if you can't fill all of the jobs, if it's not possible to get all of the jobs done, you want to find the maximum score. You want to you want to match as many jobs as possible so that, for example, the total score is maximized, or just the number of jobs you match is maximized. And you can imagine like other contexts in which this would arise. This would be like let's say you are an ads site and you have certain, and let's say these are spots for ads placement. Like somebody loads a page and there's 3 spots for ads on the page. So here are some spots for ads, and here are some potential advertisers that want to put an ad in that spot. Now, an ad spot can't be given to more than one advertiser, and an advertiser doesn't want to appear on the page multiple times, in the same load of the page. And let's say these edges now have a weight that basically says how much money you make if you make that match. Then the bipartite matching would ask, like, what is the way to maximize your gain by matching? So this is just kind of I'm just kind of mentioning this as a side note. We're not going to look at the algorithms for this one, at least not in the immediately upcoming sessions, because this is more of an advanced topic. Okay, so that's just kind of an overview of why graphs are powerful, why graphs are general, and as you can see, they can apply to a lot of different domains, and eventually we abstract something into common domain, and then we apply kind of general algorithms to solve the problems. Yep.
So I have seen a lot of mentions of directed acyclic graphs. So where is that actually going?
Yeah. So the question was, what are directed acyclic graphs, and why are they important? So a directed acyclic graph is exactly what it sounds like. It is a directed graph that does not contain a cycle. A cycle is also kind of what it sounds like. It's a path that goes around in a loop, like so. So this would be a cycle. So a directed acyclic graph is a directed graph that has no cycle. And the reason they're important is because they're one of the core concepts in this thing called topological sort. I mean, they come up in other contexts too, but one of the places where they're particularly important is in this dependency ordering problem. Specifically, it turns out that in order to solve the dependency ordering problem, not every graph has a valid dependency ordering, and specifically the graphs that do have a valid dependency ordering are only the ones that are directed acyclic. But we'll see that when we get to that topic, which won't be today. Okay, any questions on kind of this general intro that this is meant to be kind of just a general overview of the kinds of problems you can model with graphs. If you're like, hey, well, how does any of this work? Well, that's what's coming up next. So any questions on this kind of general intro before I go on to the next topic, which is how do you represent graphs on a computer? Okay. Yes.
One question is can we give multiple weights to an edge? For example, on the flight, from A to B, I have distance of 1,000 miles, and the price is $100, right? And there could be, so at that time, can it be given more than one attribute from this one node to the other node?
Well, I mean, as we'll see, edges are definitely free to hold metadata. That's just kind of arbitrary data attached to an edge. But in terms of actually using it to optimize something, well, the answer is it depends. Usually you have to come up with a certain weight for a particular edge, but you can usually consider multiple factors in it. I showed an example of that earlier where I said, well, hey, let's solve the flight routing problem by associating let's kind of say that the cost of an edge is the mileage plus 1,000 to kind of penalize the existence of paths with many edges. To kind of penalize the algorithm for selecting a path that has a lot of stops. Let's, add an artificial amount to every mileage, right? So you can do stuff like that. Otherwise, you kind of have to define what you mean, right? Because it might be kind of like a space of trade-offs, right? You can go for either flights that are shorter or flights that are cheaper, or, but, you might not be able to get the best of both worlds, right? So you would have to kind of just define what it means, and then the answer is maybe. In terms of can you solve it using a generic algorithm? The answer is maybe. It depends on the exact conditions of your problem. But if you can convert, the moral of the story is if you can convert your problem to something with one of these standard representations, you can kind of solve it right away using a standard node algorithm. And that's the power of graphs, right? Okay. So
Just another question.
Uh-huh.
Is neural networks a graph thing or?
Well, neural networks in and of itself is basically a machine learning algorithm.
Right.
Is it a graph? You could choose to see it that way. I don't think it's yeah, I mean, I think it's reasonable to kind of see it as a type of, see the network itself as a type of graph, but I don't think that's really important to the algorithm itself. I mean, and internally, like when people code it, it's often not represented as a graph. But yeah, that's kind of more about the specifics of the neural network. Well, and there's not one neural network algorithm; there's a lot of different ones, right? So the answer is kind of it depends. But usually those things are not explicitly coded as graphs. Okay. But conceptually, you can see that there's some similarities. Okay. So next topic is what do you do if you want to represent a graph on a computer, right? So let's see. So there's basically three. You might come up with others, but there's three common representations of graphs in a computer that you might want to know about. So the first is what I'll call just kind of like an edge list. So basically, this is kind of maybe the most straightforward idea. And as we'll see, it has some shortcomings. So then we'll kind of improve it and come up with another idea. But this format is actually very convenient for storing graphs in databases or serializing graphs to disk. So the idea would be that, okay, let's say we want to model this graph on a computer, right? So let's just take a sample graph, and let's say we want to model this on a computer. Well, one way would be just store the entities separately from the edges, like store edges and store entities. So you could have basically an entity table. We'll call it like vertex table, or vertex table if it's in a database or whatever. But let's call this like a vertex. These are like the vertices. We'll call this vertices. And what is vertices? It's going to be basically a map of some kind of identifier, like A is an identifier. Preferable not to use strings for identifiers, just for efficiency purposes. Ideally you'd want maybe your identifier to be some kind of long or something, long int or whatever. Okay, so basically vertices are a map of it's a map of some identifier. Let's call it's like a vertex identifier. Let's call it like a vertex, vertex ID. Vertex ID to a vertex object. And a vertex object is just an object that at a minimum has the ID in it, and probably has any additional metadata information. Like for example, if the vertices represent people, then you could think that this vertex map is going to be like a map that maps the some unique identifying ID for the person to an object that just has the person's information, like birthday, name, age, whatever. So you need some place to actually store the person's information, right? So you can just put that in the node itself, and then you have this kind of map that just maps like a unique identifier to the object itself. And then you can store the edges separately. And the way you can view an edge is basically just defined by what two things it connects. So this is essentially a map that maps a pair. It maps a pair of vertex ID1 and vertex ID2. And it maps it to an edge object. And an edge can contain any of the metadata information that you need about the edge. So, and also if there's a weight, it could be contained in here too. So the edge will have these two pieces of information and any additional information. Like for example, on LinkedIn, maybe one of the things you include in the edge on LinkedIn is when the connection between the two people was first created. You can just put whatever metadata you want to have in this edge object. And same, put whatever metadata you want to have in this vertex object. But the actual connectivity is basically modeled by what's in this mapping. Like the presence of a vertex ID1, vertex ID2 here means that between these two vertices, there's an edge. So, the representation here would basically look like a map which maps A, B, the identifiers A, B, C, and D to the actual object that has whatever other information you need about A, B, C, and D. And then on the edges here, you would have a map that maps, pairs of identifiers to whatever information is about this connection. And that could include a weight. A weight would be included in the edge object. And if you wanted to associate a weight with a vertex, you would include a weight in the vertex object. So this is, why is this, a useful format to know? Primarily because, if you were to, store a graph in, a SQL database, this is probably how it would get stored. Because, imagine, what it would be is it would basically be, you would have, an index on the vertex, you would have, a vertices table, right? And you would have an index on the vertex ID column. So you can look up by it. And then all the other attributes would just be stored as other columns. So, you would have, person ID, birthday, name, age, whatever. And then for edges, you would have person ID 1, person ID 2, and then any metadata information about edges, friendship start date or whatever. Okay. So, this is just kind of mostly this is useful because to know about, this is actually, for most problems, not the representation you actually want to be working with, internally in your algorithm. But this is useful because, that's often how things would be stored either inside a database or sometimes in, these problems where you have to read in input, from, those coding contest problems where you read in some input from, standard input or something. This is kind of a very tabular format. I described it in kind of an object-oriented way, but you could see this is a tabular format where you have, vertex ID as the first attribute, and then any other information as the other columns. So this is kind of just sort of the pure data representation, the data-oriented representation. Now, or data storage-oriented representation. Now, if you want to work with it, we'll see that this is maybe not the most convenient format. So what's good about this format is if you did build this mapping and you used some kind of efficient map data structure here, or an index in a database or something, the good news is you can find out whether if you want to quickly know if two entities are connected, you can find out, right? You can look up this key in the mapping and you can quickly find out if this is a hash map or something, in order one time you find out whether this edge is present. So that's good. You can test the presence of edges quickly. And you can also look up entities by ID quickly. But the problem here is what if what I want to do is I want to find out, what are all of the people that person 1 is connected to, right? The problem here is that, I don't really have a good way of doing that because this is indexed on both of these attributes and not just on vertex 1. So what would be better, and now you can probably anticipate the next direction, is it would be better if vertices themselves had information about what they're connected to. Because very often, and we'll see this in the BFS algorithm too, but very often a vertex will, when it's doing something, it will need to know what it's connected to. Whereas you're solving a problem and you're processing person A, you might want to know what vertex A is connected to. And it's better if you kind of have that information up front. So that moves us to our next representation. This current representation that we discussed might be called an edge set or an edge list. I will offer some, after the session, I will offer some problems on BFS for kind of homework practice for those who want it. I can guarantee you that basically you will read in data from an edge list representation as part of the problem. Usually you read the input as an edge list representation, and then you store it whatever way you want for the actual algorithm. And the way you usually want to store it for most algorithms is the next thing I'm going to discuss, which is a pretty straightforward concept. It's called an adjacency list. So in an adjacency list, you basically, again, you can have a mapping of, you still have these vertices where, you create some kind of mapping, you have a vertices map, where you create a mapping of vertex ID to some information, to vertex information. But here, in the vertex information, we're actually going to store a list of all the things we're connected to. So if we have, actually, like if a vertex has no other metadata, if there's no information about a vertex other than its identifier and what it's connected to, you can just kind of store the list here directly. So this would be kind of like storing a map, where I'll just give you what the example looks like for this one. You know, you will store some representation that looks like this. So A maps to a list that contains B, D, and C. And these are like arbitrary order. But this is just basically saying that the vertex A is connected to vertices B, C, and D. So this is just like a neighbors list of every vertex. We call these the neighbors. Like if two nodes are connected directly by an edge, like different people use different terminology. Sometimes people say they are directly connected. You know, like I kind of like the term adjacent because it's less easily confused with other terms we use for graphs. You know, we can say A and C are adjacent. That's why this is called, you know, this is called an adjacency list, and that's why. You know, sometimes I will also call them neighbors. Like B, C, and D are neighbors of A because they are adjacent to A. Same meaning. The reason I refrain from the term connected is because in graphs terminology, connected usually means like there exists a path. So like basically B and C are connected because there exists a path, even though they're not adjacent. So, you know, graphs usually when you hear connected, like people actually mean like there's a path and not they are adjacent. Okay, so then vertex B is adjacent to A and D. Vertex C is adjacent to A and D. And vertex D is adjacent to, you know, all of them again. A, B, and C. Okay, so this is just basically how an adjacency list would look like. And of course, if you have like additional metadata you have associated with each vertex, like let's say these A, B, C, D, they're like, let's say they're just like identifiers, but there's actually like, you know, information in each node, like, you know, for like it represents a person and it has a birthday, a name, this, that. Then maybe instead of this list, you want to have like what I showed before, like a vertex object. And the vertex object is one of its fields. It would have an adjacency niche. You know, it would have this like adjacency list. The vertex object would have this adjacency list, but it can also have other attributes that are just kind of like metadata you want to pass around in the algorithm. If, you know, you have an algorithm where you're doing something with that metadata. Okay. Yep.
What if it's with direction?
Oh, yeah. Good question, good question. I was actually going to get to that in like 2 minutes. Might as well get to it now. And actually, in the case of direction, it really doesn't change much. Because in the case of direction, what the change would be is the adjacency list would only mention the edges that are going in the right directions. So, for example, let's give all of these directions and let's see how it changes, right? So I've given all of these directions. Well, and let's make one of them bidirectional, like this, by putting an edge in the other direction. Okay, so this was, you know, when it was undirected. Let's see how it looks like now. So basically the key is just like, only add edges if you could actually traverse them in that direction. You know, only add adjacency if you can actually go there, right? So like, you do not put in C because there's actually no path from it. Well, not path, there's no direct link between A and C that is going in the correct direction. Here we want to basically know is like, what can we get to from A in one hop? That's basically what this is. Like, what is immediately outbound from A? So here it is just B and D. And for B, you know, it is D and nothing else. And it actually could happen for one of these lists to be empty too. This is possible. Even in the undirected world, it's possible if a node is all by itself, right? Like if there's like some E out here, not connected to anything, well, it's going to have an empty adjacency. Okay, well, you know, you probably don't need me to kind of complete all these details, but, you know, just in case, like here you have A and D, and then for D, you would have just B. So, you know, if I didn't, like, mess up this example on the whiteboard by missing something, then, you know, this would be the adjacency list for this graph. E has an empty adjacency list because E is all by itself. So for a directed graph, like, yeah, you just put in the edges that are actually in the correct direction, that's all. Make sense to everyone? Yeah, I mean, don't worry, like maybe I missed one, right, when I was putting it on the board. But you get, like, as long as you get the idea. Like, from A, you know, you have an outbound edge to B, and you have an outbound edge to D, you put it here. But you don't have an outbound edge to C, so don't put it here.
You mentioned the vertex between the graphs. Is that something like randomly generated UID or
Yeah, like it's just any like identifier by which you can look something up. Like I guess it could be like a string, like a name or something, but you want it to be like some unique identifier. So like, you know, yeah, like let it be like a UID or like let it be like some kind of like, you know, any unique identifier will do. It can in theory be a string, like of course like you might get more efficient lookup if it's just like a number. And in many algorithms, like sometimes what people will do is before running their algorithm, they'll just kind of convert all the IDs to a continuous range. Like, you know, just convert your IDs to like, well, just line up all of your entities and, you know, build a map where we're just going to say like A goes to 0, B goes to 1, C goes to 2, D goes to 3. You know, basically just map all your entities to a continuous range like this. And then after that, in the graph algorithm, you could just use numbers that are in a continuous, you know, just numbers from 0 to n minus 1 if you have that many vertices. And the benefit of that is, as we'll see, like, all the algorithms basically call for using some kind of map to access the vertices, but the map can just be an array. If the identifying keys are just in the range 0 to n minus 1, where you have n vertices, the map can just be replaced with an array. So that might be like a slight performance optimization. But basically all the algorithms are just going to call for, you know, using some kind of map to look up these adjacency lists. And, you know, a map can be an array if all your keys are in a small range, or it can be a generic map that is looked up by like a string or just the requirement is like a unique identifier of some kind. Okay, any more questions about this representation? Yeah, so like, you know, and if you have additional metadata, like, well, if it's just like one piece of information, you could make this like a tuple or something, like a pair, and include some piece of information here, like a person's name, you know. But it's probably better, like if you have a lot of different metadata, it's much better to use an object of some kind, where these are just like individual fields of the object. Where do you put edge weights if you have edge weights? Well, that's, you know, great question, if you were to ask that. So, you know, where do you put edge weights? Well, if you have a lot of metadata associated with an edge, like, I mean, the general idea is you would put it here. Like here, and here you would put some kind of like, you know, edge object. And here you would put the edge object that represents this edge. Now, in an unweighted graph where you don't have any metadata associated with the edge, like you don't need this edge, you just have the list BD. But, you know, if you have a lot of information associated with an edge, you might kind of organize it like this, where here you hold like a reference to the edge object that has all of the edge information. And it's very common to end up in a situation where, you know, where you need something like, you don't really have the information associated with the edge, but you just have like the weight and nothing else. In that case, it often makes sense to use like a pair, like for example, like a tuple, you know, with two values. So for example, let's say this weight is 5 and this weight is 10, I might represent this like that. Where, you know, this paren notation is kind of like a Python notation, which means like a tuple consisting of the entry D and the entry 5. Or 10, sorry, the entry 10. And this means this means like A has these edges. This is an edge that's outgoing to B and has weight 5, and this is an edge that's outgoing to D and has weight 10. So, you know, I kind of showed you like the generic format, which is like you put edges here, but most problems don't require like you to pass around a lot of metadata. So if you don't need that, then, you know, you might choose some representation like that. And if you don't need the weight because your problem is unweighted, then you might just have A maps to B and D. And of course, you know, another option for you, of course, is just to have this adjacency list and then have a separate edge map where you look up additional information about the edge. And those are all options, but For most problems, just something like this is sufficient.
But in this scenario, right, like if we're putting the B and 5 and the same node is again reused from another, that could be an
Well, no, this is just saying, this is actually just saying that A has outbound edges that are these two, and this outbound edge goes to B and has weight 5, and this outbound edge goes to D and has weight 10. It doesn't say anything about any other edges that are going. Like, for example, this edge, if it has weight 6, if this edge has weight 6, then it appears in this map. Yeah. So, yeah, and then there's some more entries for all the other edges.
So if I want to use the same object again, B, so it's going to be a new representation of the B object.
Do you mean a situation, by same object again, do you mean like a situation where A actually has two different edges to B? So some graph representation, like that's the only time this would even potentially be a problem here. So some graph representations, like you know, they say kind of just like, don't allow that, but, I mean, here's the reason, right? Like, let's say you had another edge from A to B with value 7, right? And let's say I'm solving some kind of shortest path problem on this graph. I can just forget about the 7, right? Because I would never use it. I would always use this 5. And so that's why usually we assume that, like, for every pair of vertices, there's only one edge, because you should be able to, like, pre-process your input into that format. Now, if for some reason it actually does matter, and you do need multiple copies, well, I mean, it wouldn't be hard. Like, I mean, hey, like, we can, you know, we can always include, like, a list here, right?
Yeah.
Like, you know, it's not hard to think of how to adjust your approach. It just kind of depends on the problem, but most of the time we kind of assume graphs will not have duplicate edges. A duplicate edge would be an edge between the same two vertices in the same direction. A graph is, of course, perfectly free to have an edge, a directed edge from A to B, and then a directed edge from B to A. That's perfectly normal, because directed graphs need to represent that kind of information, because some edges are bidirectional and some edges are not. So, you know, this is perfectly normal, but this is not a problem here. You know, this in this direction is perfectly normal, but this is not a problem here because, you know, the B's list would just have this entry. And, you know, more. Whatever else it ought to have. You know, it also has this edge to D. Okay, so this is the adjacency list format. So this is a very useful format. This is the typical format we'll be working with. Okay, so any questions on the adjacency list? This is a really important format to understand because basically most of our algorithms will kind of assume we've already processed the graph into this format. Usually what will happen is you'll read the graph in from some source, usually some kind of tabular format, like the edge list that I discussed before, and you'll just pre-process this into this format. It's not hard to imagine how. I mean, if you get there being, if you read in an edge and it says, okay, it has weight 7 and it goes from B to A. So, in other words, maybe an input to a problem consists of a tabular format like this, where every line has 3 entries, 3 tokens on it. And this is saying there's an edge from B to A with weight 7, there's an edge from A to B with weight 5. A lot of problems will kind of have data in kind of this format. Maybe you read in lines, and each line has 3 tokens like this. And so this is just saying there's an edge from B to A with 7, there's an edge from A to B with 5, and it's not hard to imagine how you put it into this format. It's pretty easy, right? You just, you start out with an empty map, and then, if your entry doesn't exist, you create it. So, you start out with an empty map, then you look at this entry, and, because your entry doesn't exist, you create it. And then you add this entry here. And then you read this next one because it doesn't exist, you create it, and you do something like this. And then if now you have something like B to D with 10, then you would see that this entry already exists, and you would just append to this list. And so this is a very common pre-processing you have to do at the beginning of most graph problems.
You mentioned if you make the node names numbers that you could use an array instead of a hash.
Yeah. Okay, so this is all this is all kind of abstract in the sense that this is just calling you for you to use some kind of map, where B is maybe a numerical identifier, maybe it may be a string. This is just an identifier of some kind. right? So in theory, your identifiers could be the numbers, like if you have n different entities, your identifiers could be the numbers from 0 to n minus 1. Right? Like you could just assign to each entity a number from 0 to n minus 1. You could line them all up and say, okay, this one gets identity 0, this one gets identity 1, 2, 3, right? And then you could just kind of, use those identifiers from there on out.
But what does that have to do with using an array instead of
Oh,
a hash?
well, think about, like, this is a map, right?
Yeah.
But what's going to happen in this map? So basically, pretty much every vertex is going to have an entry here, right? Like you have a bunch of vertices, they all have entries, right? Z, Y, whatever, right? But if these are all numbers between 0 and n minus 1, there's no need to have a map. You can just have this as an array. Like in other words, if your mapping essentially looks like this, right? There's no need to have a map. You can just put these as entry, like this. You can make this all a big array, where like the 0th index in the array has this, the first index in the array has that, the second index in the array has that.
So you've got different amounts of stuff on each index of the array.
Correct. So it would be like an array of lists, or a list of lists, or whatever. Yeah. So if all your keys are in the range 0 to n minus 1, then you have like a list of lists. Otherwise, more abstractly, you have like a map mapping the identifier to a list. And the list may be just identifiers, or maybe like pairs of identifiers and weights, or even pairs of like edge objects. Whatever, works better for your problem. Okay. Any more questions on this? Like, this is like a pretty important topic because everything will be represented in this format going forward. No? Okay. In that case, before we go on the break, I'm just going to show one more format. It's a very simple idea. This is more like, we will probably never even use this format, but this is something to be aware of because it's kind of common terminology you should know about. You should definitely not fail to know what this is. So you can also represent things in what's called an adjacency matrix. So what is an adjacency matrix? The idea of this is just use like use like a 2D array, right? So let's say you have like nodes A, B, C, D. Just imagine that they're lined up like this. And then here you basically have an array of zeros and ones showing whether things are connected. So back to our previous example. Here, let's say this is the undirected graph. Basically, there will be 1 in each spot, like a Boolean true, or a 1, if they're connected. I mean, not connected, if they're like adjacent. And there will be a 0 if they're not adjacent. So A and B have an edge between them. So this is a 1, and this is a 1, and this is a 1. So basically, this is saying that A does not have an edge to itself. Here, none of the vertices have edges to themselves. So these are all 0 along the main diagonal of this matrix. And then here we're saying A has an edge to B, has an edge to C, and has an edge to D. Then B only has an edge to A and D. So it's 1 here, and 1 here, and 0 here. And C, does not have an edge to B, but has an edge to these other ones. And then D has an edge to all of them. Okay, and you may notice that essentially this matrix, for an undirected graph, this matrix is guaranteed to be symmetric, right? So in other words, here's kind of the middle of the matrix. In theory, you could store only this part because this part is just a mirror image of that, right? Because if you have if D is connected to B, then B is connected to D, or B is connected to D, right? So this one must have the same value as this one, right? And this one must have the same value as this one. This one has the same value as that one. These are just, this is what's called a symmetric matrix for an undirected graph. And for a directed graph, of course, if you have a directed graph, you would only set to one's edges that are in the correct direction. And so then there's no guarantee that you will have any symmetry. So, for a directed graph, like here I've introduced some directions. now you will have something like, I'll just fill in the first row. So for A to go to C, you will have a 1. For A to go to B, you will have a 1. And to D, you will, well, let's say this went in the other direction, then this would be 0. Sometimes graphs may have like what are called self-loops, like, in theory you can have something like that. Like some graph formulations forbid this, but sometimes it can be useful to have that concept, so maybe in this case this would be a 1, too. But in a directed graph, you can see why this won't be symmetric. It's because just because there was an edge from A to D, like that, there's actually no edge from D to A. So when it comes time for an edge from D to A, just because there wasn't an edge from A to D, but there will be an edge from D to A. So like this is no longer symmetric. This entry is different from that entry. So just like respecting whether or not the graph is directed, you have to fill in this matrix. Like, you can think of, and it's kind of your choice which one whether you put the source or the, whether you put the first vertex or the second vertex, on top or on bottom. Like here this is like first, and this is second. So in other words, we'll call this from and to. This is like where the edge heads to, and this is where the edge heads from. Right? This is like where the edge heads from, and this is where the edge heads to. And this is just a Boolean representing whether or not it's true. Like, now why would you want this format, right? What's the point of this format? Well, most of the time this is a bad format. And the reason is, think about what would happen if this is like all of LinkedIn's users, right? So LinkedIn has, I don't know how many users they have, but let's say they have 500 million users. Maybe that's optimistic, but let's say they have 100 million users. Still, this would have to be a 100 million by 100 million matrix. In other words, it's quadratic, right? But why is the adjacency list better? Well, it's because every user is only connected to a small number of other users relative to the total pool of users out there, right? So in the adjacency matrix, you basically have an explicit value saying like, oh, are you friends with this user? Are you friends with this user? Are you friends with this user, right? But in an adjacency list, you just have an upfront list that directly tells you who your connections are. So a user might have 500 connections, and you have them right there in the list. You don't have to scan through a row containing 100 million entries for each one of LinkedIn's users, right? That would be completely impractical. So, you can imagine that for a lot of large graphs, this gets very sparse. Like, in other words, most entries are 0. Only a very, very small number of entries are positive. So you want to have them up front in the list. You don't want to have, like, this kind of representation. Now, when is this representation good? Well, this would be good if the graph is actually not sparse. Like, in other words, if most things are connected to most other things, or many other things, like a sizable fraction. Then you actually could maybe get some savings with this format. What would the savings be? Well, first of all, if you want to check whether two people are connected, you can do this just by like 2D array access, very, very fast, right? And the other advantage is that if this is all the information you have, these are just bits, right? So maybe you could really compress the information by using like bit sets and stuff like that, right? So in theory, the information content of this is only 1 bit per entry. So this is a lot cheaper than having like a list of integer entries. Like if you think about what you need, right? In an adjacency list, you would actually need like an integer identifier for each person in the list you're connected to. So that would be like, 32 bits or 64 bits multiplied by how many people you're connected to store a person. Here, you need 1 bit, but you need it for every user, regardless of whether you're connected to them or not. Okay, and then how do you use this format for like weighted graphs? It's, again, like, just put the weight in this matrix, like, similar enough modification. If you're not connected to something at all, put a special value, like, not a value, or something. Or maybe you don't want to put that, but like, maybe, all your weights are positive if they exist. Maybe this is like, time spent on a road or something, right? So, put like some special marker value if it doesn't exist. So, if you, like for example, if there's no, this is not related to this anymore. So, for example, like, if you have, let's say A does not have a path to itself, and A does not have a path, or not path, direct adjacency to itself. But let's say, A goes to C and has a weight of 8, then you would put something like that. And let's say it goes to D and has a weight of 10, then you would put something like that. But because it isn't directly, it's not directly outbound, so it doesn't have a direct outbound edge to D. You put like a special marker value here. Or if that doesn't work because there's no special marker value you can use, then you could have a separate matrix like one that's Booleans that tells you if you're connected, and another matrix like this that has the weights in the case that you are connected. In the case that you are adjacent to those vertices. Okay. So, this is just a format you should know. This is not a format you'll be using particularly often because most graphs are actually sparse. Like, a lot of the most useful kinds of graphs are actually going to be sparse. Like, every user is going to have, like, 500 other users they're connected to, and nowhere close to, like, all the possible users out there. But sometimes if you did have, like, a dense graph, like, some format like this could be useful.
So even if it's fairly connected, if it's not directed graph, then there's no point, right? Using this. So half the matrix will be anyways be wasted.
Okay, so if it's undirected, then, you could just store half of the matrix. You could still use a matrix, you could just store only half of it.
Oh,
Because, if the matrix, if the graph is undirected, that means it's kind of symmetric across this line, right? So then just store the lower half of it, or the upper half of the matrix. Or if that's inconvenient, well, it might be inconvenient to do that, but, Okay. This is just a format I want you to be familiar with. It's called an adjacency matrix. Sometimes you do see it. You mostly see it in, maybe some, coding contest problems. And then it's not a big deal. Usually the first thing you want to do, for most problems, I mean, there may be some exceptions, but most problems, the first thing you do when you see an adjacency matrix is just convert it to an adjacency list. That's usually the answer to most things, just convert to an adjacency list, and then all the algorithms we'll discuss will run against an adjacency list. But it's always easy, it's a pretty easy data operation to convert one format to another. The adjacency matrix is just bad because it has an explicit entry for every pair, right? And that can be bad because it's quadratic. It uses quadratic space with respect to the number of entities you have. One just small point I want to mention. So when I mentioned the adjacency list, right, I kind of wrote it in this kind of format, where there would be a map that maps the identifier to a list of things it's adjacent to, right? It showed this kind of format. For most problems, this is sufficient, because for most problems, you will only need to know, for each vertex, you will need to iterate through all of its neighbors. And then this is sufficient. But what if you wanted to do the same kind of thing you do with an adjacency matrix, where you can actually check quickly if two vertices are connected? So let's say I wanted to quickly check if A and D are connected. Well, then maybe just this by itself is not so good, because we can imagine this list is very, very long, and it'll take me a while to find the speed in this list, right? So in that case, there's a very easy solution. Just do adjacency sets instead. You can make if you do need that capability of quickly checking whether two nodes are adjacent, just make it into a set. And then if I want to know if A and B are connected, I will first look up A, I will get this adjacency set, and then I will look up B in the set. This is just if you need to, if in addition to being able to iterate through all of the things that a node is adjacent to, you also need the ability to quickly check whether two specific things you already have in mind are adjacent. Then you do need this to be a set, so you don't have to do a linear scan through the